Hello everyone, Sean from Having Fun Repairs. I wasn't originally planning on doing a video, repair video on this, but after starting work on it, I figured, why not? So this is an Ibanez Troubadour guitar amplifier, model number TA35. I believe it's a solid state amplifier. Transistor or MOSFET driven amplification versus tube driven. However, I've not been in it physically inside this product at all. It was being used at the church we attend by a pianist. However, when she was playing, a bit of difficulty getting sound out of the amplifier, mostly due to this jack here. So just have my guitar plugged up to it for right now, but a little bit of QD electronic cleaner and wiping out inside of here seems to resolve that issue. So you used to have to put pressure right on the left side to get contact. Now I'm probably still going to take it apart and just fiddle on the inside of this jack a bit. This 1/4 inch phono jack or audio jack. Just get the leaf springs on it a little bit tighter, so that way there's not so much play. Forgive all the kids in the background. Not so much play, and it doesn't lose connectivity again. And I'm not doing this for any type of monetary gain. Typically with all my videos, I'm not doing anything and selling anything. I just do it for the fun of it. So to me, this is just a bit of charity work, and what I owe for a congregation that's been very supportive of me and my family. I've got another amplifier that I do need to get repaired. Because audio is cutting out, there's definitely some problems with it. But I wanted to plug this up and run through a few tests on this. Now, I couldn't find a service manual for it per se. I did find an owner's manual, and there were some things that we could check out via the injecting a signal and looking at some things on the oscilloscope. First being the bass level. Now I pre-recorded what the original settings were so I can return back to nominal. The bass level is supposed to provide amplification of plus 15 or minus 15 decibels at 70 hertz or less. So with a 70 hertz or less signal injected into here, I should be able to decrease it and see that 15 dB drop approximately, I would assume. Increase it and see a 15 dB gain. Your middle frequency and middle level. Now this is frequency selected, so whatever I set this to, if I set it to 1 kilohertz, then I should be able to amplify or decrease the amount of gain of that 1 kHz signal. So this one is selectable between 400 hertz to 2000 hertz. So depending on what frequency I have this selected to or tuned to, that is the frequency that's going to receive the amplification. So we got two things that we can test with this. We can test that the amplifier circuitry is working correctly. We can also test that when this knob is tuned, if whatever tunable cavity or filtering circuitry, if I can put it that way, is actually tuning to what's on the dial. And then treble, again, that's going to be anything 8.7 thousand hertz or 8,700 hertz or 8.7 kHz, excuse me, plus or minus 15 dB again. So what I wrote down is we'll test at 65 hertz, 1 kHz, and 10 kHz, as well as the mid-range frequency adjust knob to see if it's tuning appropriately. Now, I don't plan on fixing anything that's out of range, because like I said, the only issue was this, and so I'll tackle that. And the settings on this are typically with what I pre-recorded down: bass and treble, pretty low range. This was around 1 kHz. At unity gain, meaning 0 dB of gain or 0 dB of loss. So, and it just plays that way. So, my only concern is, I will show you these tests. I'm not too concerned if they're out of range, out of issue. It's not something I'm going to repair. My main focus was this. But I wanted to demonstrate this for you anyways, and hopefully you got something to gain. So, let me put my guitar away, unplug it, and set it aside. Alright, now that I've got that set aside, I've got a cell phone here generating audio signals. I'm going to set it to that first one. It said 65 Hertz. Oh. Ads, what's going on here? $65. Now you're not going to hear this because I currently have a something plugged into the audio jack, but I should be able to stick this into the front here, and you can hear that tone coming out of the speaker. Now I'm going to unplug the speaker from the back, and this is the speaker resistance is 4 ohms. I've already tested that. It's around 3.8 ohms of resistance, so call that good. I'm going to take this 1/4 inch audio jack, plug it into where the speaker out of the amp would go. Now I've got that fed up to this other end. Got the sleeve pulled back, it going to no scope probe set to 1 by or 1 times, and then get it up here on the oscope itself. All right. So let me turn down my volts per division a bit. I think right there will be good. And we will double check. Bass is set to 0. Okay. This is going to be, we see down here that the oscope is measuring the frequency at around 65 Hertz, which is what we are sending out the phone anyways. And we're going to take a preliminary measurement at that range with the knob set at 0 of 240 millivolts, and let me write that down. Excuse me, 240 millivolts. This is nominal, so nom 240 millivolts. Alright, now that voltage will increase if I increase the master volume knob or the input volume knob. But I want to leave those alone for these types of measurements. Now the next thing I'm going to do is I'm going to turn this counterclockwise, just the bass knob, and I want to take a look at my signal at the same time. I want to make sure it doesn't completely drop out or I lose anything as I'm decreasing the amplitude of that signal through that specific knob. Now, I need to turn this down a little bit. Where's my trigger at? Keep it triggered right there. It's keeping it a bit steady. I guess I could move this up a bit so y'all can see that. Alright. Now we're still right on frequency in our volts RMS. We're measuring 40 millivolts. So at -15 we equal 40 millivolts. Now we need to check +15. We just turn the knob clockwise from 0. And the same thing. Set this back to 0. Oh, I need to change my scale again because I'm now way off scale. And we'll start increasing it. On here, again, keeping my eye on that waveform while I'm turning it. I don't want to see it cut out at all. It means we got a dead spot on the potentiometer. I also don't want to see any clipping as I increase. I want to, sorry, I backed off just a bit because I need to change my scale. Now by clipping I mean flattening of our peaks, okay? I don't want to see any audio clipping. And we'll keep increasing it. And we get frequency still within range, I would assume. You know, that deviation is probably either due to the characteristics of the oscilloscope or my cell phone producing the frequency. We got up to 1.2 volts RMS. Okay. So +15, we're at 1.20 volts RMS. Now, remember what I said, base level plus or minus 15 dB at 70 hertz or below. And dB is just, it's relative to whatever measurement you're taking. As a matter of fact, I can show you this on, instead of doing the math, and there is a formula for it. I'll go ahead and say that when you're dealing with voltage, every 6 dB you either half or double your voltage. So for instance, if my input voltage is 1, my output voltage is 2, and I click calculate, you can see that has a 6 dB of gain. Okay, so if you want to keep that in the back of your head, whereas if I was at an input voltage of 4 and my output voltage was 2, you'll see that as 6 dB of loss. So obviously if I go from, say, 2 to 4, 4 to 8, that should be 12. Yep, 12 dB of loss. If I go 1 doubled to 2, 2 is doubled to 4, that should be 12 dB of gain, right? Vice versa. So that's how you do voltage. Now watts, traditionally you'll see watts in relation to RF output power. Watts is not 6 dB, it is 3 dB. So let me change this to 2. Calculate. There you go. I'll change that for comparison. So you can see that difference right there with watts. Anytime I double the amount of power out, it has a 3 dB gain. Or vice versa. If I half my power, output power, that's 3 dB of loss. And again, 2 to 4 would be 3 dB. 4 to 8 would be 6 dB. And you could just reverse and get the same thing. Okay, so that's like I said, dB is just in relation to what type of metric is associated with the measurement, whether it's voltage or wattage. But anyways, kind of going off on a tangent here. We had at 65, our nominal voltage was 240 millivolts, so 0.240. And when we went to the negative 15 position, we dropped down to 40 millivolts. So, we are seeing that we had around 15 dB of loss. And then in reverse, went to positive 15 on that, 0.12 volts, or 1.2, sorry. You got about 14 dB of gain. So not quite 15 out of there. I would suspect that there is probably some issue in whatever is driving the gain, that circuitry, whether it's transistors or whatever happens to be in there, whatever component. It's probably got a bit of age to it. If this was, you know, something I felt like I was going to spend the money on, which I'm not going to spend money to refurbish this amp. I'm just going to correct the audio in issue, which I did, and try to keep it from coming back. This would be something I would look into, because this could potentially be an issue in the amplifier section. Now again, I don't have any of the tech data, but to be a whole dB, essentially 1.1 dB off, that to me is probably slightly out of tolerance, but what do I know? Okay, so we're going to repeat this process again. For the mid-range frequency. Hello everyone. Kind of interjecting for a second before we get into this next alignment, because I'm coming from the future of that alignment, and I realize that, you know, to me, as I'm trying to demonstrate what I'm doing and showing what I'm adjusting on the equipment and the oscilloscope, that it would probably be best if I give a bit of an introduction by drawing out on a paper what exactly this alignment is about. Now, in your mid-range, you have essentially a frequency range switch that allows you to tune to the mid-range frequency you want to provide amplification to. So I've drawn a line at the bottom to represent that specific switch. Okay. And it ranges from 400 to 2K hertz, 400 hertz, 2K hertz, and mid-run is around 1000 hertz or 1K hertz. Okay, now on this top range, this top bar, we're going to say, and this is just me making up, if 0 volts is at the bottom, approximately 240. I think that's what a lot of the measurements came to. Millivolts would be up top. Okay, and now I'm going to draw a bell curve right around this 1K hertz mark to the top. Okay, and that bell curve would look something like this right here if I was to take that frequency and look at it on a spectrum analyzer. Okay. Now, on each side of this frequency, this should be of equal distance, but at the center point of the frequency, I should be at max amplitude concerning the measurement, or 240 volts. Let me zoom in a little bit more. Might be out of focus. Now, what I'm attempting to do in this measurement, or under tests, is determine if the frequency on the dial actually represents the frequency that I'm injecting into the equipment. So as the dial sits on 1K hertz, I want to know that when I am increasing, when I take the mid-range frequency switch and set to 1K hertz, I want to know that the second switch dial, as I increase the mid-range amplitude from bottom to top of that frequency, that I am actually increasing the amplitude of the frequency that's on the dial. So if the dial is correct, then when I'm increasing amplitude, that means that I am only increasing the frequency that I've selected. Okay, which would go up to whatever is that next range, 280 millivolts, whatever. All right. Now, as I go through this process of slightly amplifying and adjusting the dial, what I actually learn, let me draw a bell curve out here to the left. We'll just put a mark here, and I'll make everything dotted lines. Okay. As I'm doing this test, I'm actually finding out that at the max amplitude, while injecting a 1 kHz signal, it's actually showing up on the dial somewhere over here between 400 Hz and 1 kHz. So that's telling me a few things. It could be that the potentiometer it may have aged. It could also tell me that there are potentially components inside, filters or voltage control oscillator or something that is going to actually result in the frequency that I've selected on the dial, that accuracy is not correct. Okay, I can put it that way. So there could be some components internal other than the actual potentiometer itself that are an issue. But anyways, I demonstrate that, and we will, hopefully this helps out with the understanding, and we will get back to that portion of the alignment. So what I've got to do is I'm going to set this back to 0. These are both up here. I need to change my frequency to 1 kHz. So let's do that. So 1000 Hertz. Still there. Now, we can tell that mid-range control right here. Might need to turn on a light. Hold on a second. See, the knob is sitting right there at about a 1 kHz or 1000 Hertz. I got this, the level zeroed out. We can now come back up to my oscilloscope. Ooh. Let's get that turned up a bit. Span per division, horizontal, vertical. All right, what do we have? So at 1 kHz, we're measuring it there in the lower hand corner. Volts RMS is at 100 millivolts. We'll make that our reference voltage. So I'll need to write that down. So at 1 kHz, our reference voltage, or nominal for right now, it's 100 millivolts. Now, before I start testing the amplitude of it as I increase or decrease gain, I want to see if the frequency selector switch is tracking. Now, let me show you something real quick. While this is at unity gain, meaning we are not adding to or decreasing that 100 millivolt amplitude. Nothing I do on this frequency switch, if I go left or right, it should change that amplitude at all. See? It's only when I decide to give it a little bit of gain. You see that. Sorry, probably should have demonstrated that. Put it back on 1K hertz. See, there goes at 0. I'm going to give it a little bit of gain. Now, I want you to watch what happens as I turn the frequency control counterclockwise and clockwise, right? Now, I am on, according to that dial, 1000 hertz, still a slight bit of gain. Okay? And as I take this and turn it counterclockwise and clockwise, I should at no point see that amplitude increase on that 1K hertz signal. So as I go counterclockwise, it should not increase. It should only start coming down. Now look, I've gone fully counterclockwise at this point, and it did come down. Now, actually, what I want to do is give it a little more baseline amplitude. So I got a stronger signal going into my SIGGEN first. So we'll restart that. Let me restart it. Alright, I made nominal 240 again. Now we'll give it a little bit. Increase the amplitude just a little bit with that control over here. Alright, so we're at 248. Now as I turn this clockwise, if that frequency selector switch is tuned, whatever that tuning control is perfect, I should see that amplitude start to decrease. 240, and I'm going very slow to the right. See it drop down 232, 224, yeah, 216, going back counterclockwise. So that's good. Like at 1K hertz, when I go clockwise, at no point in time did the amplitude increase. It didn't get larger. So as I was going off frequency, then then the gain I was given per that frequency was no longer being applied because I was changing the frequency. I was going from 1K up to 2000 hertz. So it makes sense as I move closer to 2000 hertz, the less gain I would see on my oscilloscope because I was no longer on frequency. Okay? Now the same thing should occur as I go counterclockwise. So let's do that. We're at essentially 248, pretty close to that 1K hertz. Now let me turn it counterclockwise. And I'm just doing this ever so slightly. Not turning it super quick, turning it super slow. And after every segment of movement, I stop and I watch. And then, hold on a second. I've moved slightly counterclockwise, off center freak, and you see that voltage increase to 256. Let's take a look at where that's at. So with the voltage increase going off frequency, see, like I said, slowly, stop, watch. So I turn slowly a little bit, and then I stop, and then I look, a little bit, stop and look. But I see that my amplitude is increased. So I don't know how much slop is built into the tuning circuitry for your mid-range. But essentially your 1 kilohertz is not on dial, it is off dial, which is why you saw the amplitude increase even more. Now this was not adjusted at all, this stayed exactly the same. So that means that I got more on frequency by going off dial, which means that this probably has a bit of wear in its tunable cavity or whatever frequency select or filtering circuitry is built into the mid-range. Now I wonder how much more, if I continue to go off frequency, will it continue to increase or will it decrease? We can watch that up on the scope. $264. Now we're back down to 256. So we go up even more. Then we start coming right back down to 248, 240, 230, 216. Alright, so now what I want to do is I want to find that peak. Meaning that point where it is at the highest amplitude. Okay? So I'm going back towards center, and now I'm starting to turn slightly clockwise again. Sorry, counterclockwise. 264. Keep going counterclockwise. 256. Now I'm going clockwise again. 264. 256. Now I'm going counterclockwise again. 264. All right. So essentially this could be an issue inside this amplifier. That would be, again, if I wanted to spend the time to refurbish the entire amplifier, that would be something I'm looking at, because I am sending in a 1 kHz signal, and when I have this on selected for 1 kHz, I expect that's what I'm amplifying and that's what I'm attenuating. But in all honesty, 1000 Hertz is somewhere over here on this scale. Alright, but now we know where that 1 kHz is at. Now we can test our level gain, and that's the next thing we need to do. So nominal again, 240. Let's go counterclockwise down to -15. Change my volts per division, make sure that has an accurate voltage measurement. That's sine wave. It's not all that good looking. I would expect it to be a lot cleaner than that. So that could be another potential issue. But anyways, fully counterclockwise, we're at 30.4 millivolts. So -15 is at 30.4 millivolts. Started out with 240 millivolts. Go back to increasing the level. And I need to change my volts per division scale. back to 0. Start amplifying it. Just go again. Alright. You see, as I increase gain, that signal gets a lot cleaner. So I don't know if that's just a characteristic of the amp, or maybe that's just frequency is getting a little bit ugly. Again, could be an issue. What's our max voltage now? 880 millivolts. It's millivolts AC. I'm taking the root mean squared instead of peak to peak, because that's going to be your average voltage. I prefer to do that over peak to peak, which is your actual bottom to top voltage. And we'll plug it into here, see what we come up with again. So give me a second. Alright, with a 240 millivolt reference, we went down to 30.4 millivolts, so 0.0304. So we had a decrease of 17 dB. I would call that good. It's, in my head, it's okay to have more gain and more loss than to have less gain and less loss. So if you're supposed to have 15 dB of gain and you get 17 dB of gain, that's good. But if you're supposed to have 15 dB of gain, you only get 13, that's bad. Same thing with loss. I'm supposed to at least have 15 dB of loss. If I got negative 17, that's good. If I only got negative 12 or 13 or even 14 in my head, it's probably bad. Let's check the upper range now. 0.880. Again, on the upper end, we're only getting about 11 dB of gain. So we're seeing some commonality between amplification at our bass range, our mid range, and I wonder if that will carry over to the high range. So the next thing we got to do is set up for high range, which is any frequency greater than 8.7 thousand, or excuse me, 8.7 thousand hertz. So we'll just do 10,000 hertz. Let's add another 0 in there. Alright, now I should be getting 10,000 hertz. My oscilloscope is saying I'm getting 10,000 hertz. Let's set this back to 0. Treble control needs to go to 0. Alright. Treble control at 0. 10,000 hertz going in. Span per division. Okay. I am measuring 1.2 volts. So I'll write that down as my nominal. 1.2 volts. And we're going to run through this again. Counterclockwise down to negative 15. Keep an eye on that waveform. Yeah, even up here you can see when I go negative, that signal starts to get a little distorted. I wonder if it will be as bad all the way at the bottom. Clears up a little bit on that pot. Could also just be the potentiometer. Pretty sure there's a voltage going through the potentiometer that's biasing something to create that amplification. See, it gets a little distorted up through that range. Could be just a condition of that potentiometer. Could need some cleaning. But anyways, let's see. At -15, we are measuring 540 millivolts. Now let's go up to the +15 side. And it is clipping bad. Look at that. That's what I'm talking about. That's what I do not want to see. So there's definitely... Yeah, I get like next to no amplification. 10 kHz and above. Now I don't know if it's characteristic of this amplifier through that frequency range. Or if it's an issue meaning this amplifier can't reproduce anything that high in that frequency range. Again, without tech data, I don't know. But that'll be a very distorted 10 kHz audio signal coming through. It wouldn't sound perfect. It would sound very messed up. About the max increase I get is 1.4 volts. So I already know that that's going to be an issue. Let me put that back in nominal. And we'll do the calculations again. So we started out with 1.2 volts at -15. We saw 540 millivolts, so 0.540. Not quite 15 there, so that's not good. Only 6 dB of loss. Which makes sense, 0.5 plus 0.5 is basically 1 volt. 4 and 4 is 8, so you got 1.08 volts, right? Remember what I said? Half your voltage, 6 dB of loss. Double your voltage, 6 dB of gain. So let's just for giggles, 1.4 was the gain. And we only saw a dB of gain through that entire range. I kind of want to drop that frequency down a little because it's what, 8.7 and above. So what if we made it 9,000 hertz, essentially 9,001. And we did the same thing. What would we be getting? In reference, 1.16 volts at 9,000 hertz. Counterclockwise. Yeah, pot definitely needs to be cleaned. Look at it, so nasty. 48 millivolts or 480 millivolts. Yeah, we're still not there. So let me guess, clipping. Yep. and it's clipping. So definitely issues in the amplification circuitry. Could be the potentiometer as well, but with that clipping, I would expect a potentiometer to create these types of issues if they're dirty, if you don't have that nice pretty bell curve. But clipping comes from some bad ICs or transistors or whatever's used to amplify that signal. So that's where that's at. And what I'll do now is I'm going to take apart this amplifier. I'm not correcting any of these audio issues. I'm only going to fix the audio jack. I'm going to take apart the amplifier. I'm going to clean out the inside a bit and mess with those leaf springs. So let's get this thing apart. Well, I think we've gotten quite a bit done so far. We've done a lot of pre-testing and verification of some of the amplitude controls in our mid-range frequency switch. We're seeing some issues outside the one reason why I took the equipment, the 1/4 inch jack, when the piano was plugged in, being a little iffy. And that's pretty much where we're going to stop on this video, and we'll return back with the next part. I will have the amplifier taken apart, and we can begin a little bit of troubleshooting and go from there. So if you've liked this video and you found it pretty informative, please consider giving it a thumbs up and subscribing to the channel, and sharing it with folks who you think might have a general interest as well. Again, none of that ever required, but I definitely do appreciate it. Alright, take care. Bye.